matrix into the intermembrane space. So I said in the chemiosmotic production of ATP, electrons flow through of the membrane energetically downhill, which means a spontaneous flow. We're moving from high free energy to low free energy. We know that if delta G is negative, things happen spontaneously, right? And so this is a negative delta energetic free energy process. They're going to flow spontaneously from the activated carrier to complex 1, to a carrier in the membrane, a lipid carrier, to complex 3, to complex 4, to another carrier, okay? And then they're going to find their final destination with oxygen. They're going to make oxygen very negative, which will attract protons to make water at their low energy state. And as the electrons flow through these protein complexes, these complexes act like proton pumps. And they pump protons from the matrix into the intermembrane space. So as I've said already a few times, the electron transfer chain, the energy of the electrons flowing downhill, that energy is used to create a proton gradient. High proton concentration here, very low here. So which one has a lower pH? A or B? Where is the pH lower, more acidic? Here, with my right hand or left hand? Here, right? More protons and more acidic, right? That's real basic stuff, okay? That's third grade stuff, okay? Now these suckers are charged. These are ions, okay? There's a pH gradient. A low pH, a higher pH. That essentially reflects the high proton concentration here compared to here. We know that if you have a gradient across a barrier, they want to tend to diffuse down the concentration gradient, right? Okay? There's a concentration gradient, but there's also an electrical gradient. Because the inner side of the membrane is slightly negative, and so these protons are also attracted to the matrix because of this opposite charge attraction. Therefore, combined, the concentration gradient and the voltage gradient combine to produce what's called a proton motive force. It's the sum of the pH gradient between the intermembrane space and the matrix, and it's also in part due to the voltage gradient. Because the inside of this membrane here in the matrix is negative, and all these protons are going to make this positive. So they combine together to want these protons to move from the intermembrane space into the matrix. It's water behind the dam. But protons can't diffuse through a phospholipid bilayer. Especially, I told you the inner membrane here has those special lipids that really minimize leakage. I told you that the phospholipid head with the 4 fatty acid tail is really packed in tight here. So the only pathway through is through this rotor here, ATP synthase. And this is the turbine. And this thing mechanically spins like a turbine. As the protons flow through here, that rotation triggers the linkage of high phosphate onto ADP to make ATP. And it takes 4 hydrogen protons, 4 of these to flow through to make 1 ATP. 4. Okay? 4 protons make 1 ATP. We'll do a little bookkeeping here. Now, check out a few things here. Now, if you look at where the activated carriers deliver their cargo, NADH, and how many NADHs do we make in one cycle, turn of the Krebs cycle? 3. So, with one turn of the Krebs cycle, I'll put KC. It doesn't stand for Kansas City. Okay? We make 3 NADH. Now, I'm not talking about pyruvate oxidation and other things. I'm just talking about the acetyl oxidation of the acetyl group. Okay? 3 NADH. How many FADH2? 1. Okay? Now, NADH delivers this cargo to complex 1. When the electrons, these 2 electrons flow through here, they result in 4 protons being pumped into this space. Okay? And those 2 electrons yield 4 protons being pumped into space. Let me check my. I have that on this slide. No, I don't. But I'm pretty sure that's right. Okay? So 4 protons are pumped here. Okay? Then those electrons are shuttled via ubiquinone to complex 3. As the electrons flow through here, there's another 4 protons pumped through here. So now you've got 8 protons in there. Okay? And then those electrons are delivered one at a time via cytochrome C to this 4th complex. And this will pump 2 protons. So for each NADH, they're going to send 10 protons into the inner membrane space. Okay? They're pumped into the inner membrane compartment. Okay? Now I said it takes about 4 protons to yield 1 ATP when they flow back through this rotor here. So how many? So per NADH, how many ATP do you get? What's the yield for ATP? So each NADH, when it's oxidized, when it sends these electrons through this pathway, it ends in the result of 4 and 4. Let's see, 4 and 4 is 8, and 8 plus 2 is 10. I got that right. And it takes 4 H plus is flowing through here, 4 of these flowing through here to make 1 ATP. So per NADH, how many ATP do you get per NADH? What's 4 into 10? Did I do the math right? So every NADH produces 2.5 ATP on average. Okay? Now FADH2, it doesn't do quite as good of a job. Okay? If I go back one here, let me go back and make a point here. This enzyme here, succinate dehydrogenase. Gotta say that carefully. Okay? It's a redox reaction. You know that from the name of the enzyme. It strips electrons from this and adds them to FAD to make FADA. Okay? Alright? Okay? Now this enzyme, succinate dehydrogenase, is part of complex 2 in the transport chain. It's part of this complex here. And this is where FADH delivers its electrons. It's 2 electrons. Okay? Okay? And that's because that succinate dehydrogenase, remember, those enzymes can work in 2 directions. It can reduce FAD to FADH, as it did in the Krebs cycle, but then it can here oxidize FADH to release FAD and send the electrons here. Does that make sense? Because I told you that enzyme is attached to the inner side of the matrix side of the inner membrane. It's the only Krebs cycle enzyme that's not freely dissolved in the matrix. So it reverses that. So as part of the Krebs cycle, it reduces FAD to make FADH2. As part of the electron transport chain, it oxidizes FADH2 to release the electrons. Then they flow through this lipid carrier through complex 3. How many protons will it pump over here? Those 2 electrons? 4. And then when those 2 electrons move one at a time through into the complex 4, it'll produce 2. So for each FADH, these 2 electrons will produce 6 protons into the intermembrane compartment. If it takes 4 protons to make an ATP, what's the per FADH, what's our ATP yield? What's 4 into 6? So because FAD is delivering the electrons at kind of a lower level, lower free energy level, at this position here, it's going to yield pure ATP from the electrons it's carrying. Okay? Because it's entering the transport chain further downhill. You see that? Here's the top of the hill, it's further down here, for the that energy landscape. So it's gonna, electrons it's extracted from the Krebs cycle reactions, it produces only one per FADH, only 1.5 ATP versus NADH, which yields you 2.5 ATP per NADH for the 2 electrons it delivers. Okay, are you lost? Let's talk about some of these. Now, all these little circles in here. Okay, these represent some of the components. This is not one protein. This is, I think in total, if I recall, like 40 plus proteins make up these 3 complexes. Okay, the electrons are mostly transferred from one protein metal complex to the other. Metals are good at holding electrons. You notice metals are good conductors of electricity, so they're able to handle electrons and pass them on. Okay? Early in the pathway is mostly iron-sulfur metals. Okay? Sulfur's not, well, sulfur's kind of irons are definitely a metal. Okay? And as they move further along the pathway, the carriers are what are called cytochromes, and they have a heme unit with iron. Okay? So these are metal protein carriers that actually allow the electrons to flow. And a complex 3 is actually a combination of heme and copper that kind of hold the electrons and pass them to oxygen. And this last step is pretty critical because the 2 electrons released by each carrier kind of travel together. Okay? But when they get to cytochrome C, they can only be delivered one at a time to the cytochrome